thank you very much for the organizers for putting together this very interesting program and for giving me the opportunity to tell you a little bit about some of the research we've been doing in my group. I had submitted a much longer title, more detailed, maybe more complicated. When I looked at the program, I found it shortened to this, and I thought, just like you don't argue with an editor of Nature when they're willing to accept your paper and want to change your title, I thought, I'm not going to argue with the organizers, and basically this is my talk summarized in a smaller number of words. So yes, I will tell you about some work in which we discovered that you can sort of reproduce the observed radius valley that separates the super-Earth and the Sub-Neptune population just from a planet formation point of view. So thanks to the two very nice previous talks, I don't really have to do much introduction. So the population that I'll be talking about are the super-Earth and Sub-Neptunes, these planets that as of to date are the most common planets that we have been discovered. They're almost everywhere, as I'm sure you know. And they're intriguing. They were intriguing for me for a long time, somebody who's been studying planet formation for many years, because these planets are so different from what we have in our solar system, right? Typically, they are in between the size of Earth and Neptune on orbital periods that are well within the orbit of Mercury. In addition, we know for several of those planets that their radii are so large, given their masses, that they must have about a few % of the total mass budget is sort of a hydrogen-helium envelope. And so we were just curious to see whether we can understand the formation of these planets by sort of self-consistently treating the gas accretion and the subsequent evolution and loss from those planets. So here we go. So when you form a planet, you start accreting a core in the disk. One of the key things you need to do is, right, you need to basically, you're converting loads of gravitational binding energy into heat as you're accumulating your rocky core. And this heat can very effectively be transported away if you're doing this in a disk when you initially have a very small body. If that body is smaller than basically the Bondi radius, so the radius where the thermal speed equals the escape speed of your planet, if that's inside the physical radius of the planet, your gas will just flow by, carry away the heat, and you can very efficiently cool your growing embryo. However, once you grow a core where basically the physical size of your planet becomes comparable or smaller than the Bondi radius, then you start holding on to the gas, because now there is a region outside the physical core radius of your planet up to which the gas will be gravitationally bound to you. And once this happens, you're still accreting your core, so you're still heating your core, but any of that heat can no longer easily be carried away by the gas flowing by. But now the gas that you're accreting and holding on to starts to act like a thermal blanket. And now you have to think of your planet as a coupled system, your atmosphere and your core. And so as a consequence, the cores that are underlying these hydrogen-helium envelopes sort of have the maximum temperature they can have and still hold on to a hydrogen-helium envelope. Because they'll be any hotter, the envelope will be unbound, and then you could cool until you bind that envelope to you again. And so you know that the temperature of these cores is between 10 to the 4 and 10 to the 5 Kelvin. Now it depends on whether you are an Earth or 10 times the Earth in mass. And then on top you have sitting this hydrogen-helium envelope. So what's the structure of this envelope and how do you create this envelope? So initially you just have whatever is bound within your Bondi radius. And you can do some simple math and count up how much mass that is, and you find that's typically less than 0.1% of the total planet mass. So it's cute if you just want some envelope, but it's not enough, right, to form these Sub-Neptunes, which have like a few % of the total mass in hydrogen-helium. So you have to do something else to accrete more gas. So what is the something else? The something else is that you just have to wait a little bit for your envelope to cool and contract. As your envelope starts to cool and contract, you can pile on more gas on the outside, and so your planet can keep growing its envelope mass. So in detail, what you have is your envelope structure is mostly adiabatic because the energy is being transported by convection, but then you start developing a small outer radiative layer that basically is where your envelope shrinks and contracts such that you can accrete more material. And so interesting enough, in this phase of gas accretion, your accretion is basically just limited by cooling, because if you can cool faster, you just can accrete more gas faster. And so what is nice is, with this understanding, you can write down what the typical envelope mass that you can accrete is, given other parameters of your system. So that's what I've shown here. F is just a fraction of the total atmospheric mass to the core mass. And you can see, not surprisingly, it scales as the mass of a planet because of your Bondi radius, right? If you're bigger, your Bondi radius is bigger. So you have more region to hold on to an atmosphere. It scales to the disk lifetime because it sets the time scale you have for accretion, right? And the opacity, and specifically the opacity at the rate of convective boundary, where you connect the radiative region of your envelope to the isothermal radiative region, because that's the bottleneck for cooling, right? Any heat that wants to escape from the inner envelope and your core needs to basically go from the optically thick to the thin part at this rate of convective boundary. So this is zero order, how you can understand this. And the good news is, for typical disk lifetimes on our planet masses, you can indeed accrete several percent of the planet's total mass as hydrogen helium. So that's great. One cute side note, because the outer layer of your planet, they're almost isothermal, and therefore they have a close to exponential density profile. So the amount of atmosphere you accrete is actually only logarithmically dependent on the gas disk density that you have, because that's only how it enters basically into the accretion. So it's not super sensitive to those details. So that's sort of a nice thing. But okay, so we should be happy. We can accrete our atmospheres. Turns out we don't get to keep all of the stuff we have accreted. The first thing that's going to happen to us is the following. The gas disk will go away eventually. And if this happens, basically you lose the pressure support in the disk. And so basically, if you now look at your planet, the outer regions of your atmosphere, because you remove the gas disk on the outside, will want to expand into vacuum. Just because they can. And because of that, and because there's plenty of energy in the inner parts of the envelope, the planet will shed several tenths to up to 70% of all the gas it just has accreted during the disk dispersal phase as the gas disk goes away. And so as a result, you not only lose several tenths of percent of the envelope mass you just accreted, but your planet also fairly rapidly can shrink in size to sizes that are just a few times the core radius, rather than these very large radii that are comparable to the Bondi radius. And that's because, right, mass loss takes away energy, and therefore the remaining material can cool and shrink more quickly. But it's okay, right? We still get, this is what you're left with after this dispersal phase. You're still fine because you still get a percent or a few percent for your typical planet cases. So just remember, if you ever want to form these planets, just make sure that you can accrete about a factor of 2 or more in your initial envelope mass than you need, so that you're okay with losing about half of it during the gas dispersal phase. What happens next was sort of interesting, and that we didn't really expect it until we thought about it in detail, was now we thought, well, probably we're good now. We get to keep the rest of the envelope, and we're done. And in some cases, this is actually true. So what we discovered is, from then on, there are 2 different pathways for your planets. There are 2 different regimes in which your planet can cool and contract. So I'll tell you about the more obvious one and the one that has been studied in a lot more detail first. So in the first regime, when you look at the total energy budget of the planet that's available for cooling, if that's dominated by basically the thermal and gravitational energy in your envelope, in those cases, your planet will indeed, from then onwards, just cool and contract, and you get to keep the atmosphere you have accreted. And this is, many of our solar system planets are still in this phase, and this cooling time, right, can take gigayears, and your planet just cools and contracts. If you look at the profile, right, what happens is the rate of convective boundary will just move inward in time, and the isothermal region will expand, and it's all good. When are you in this regime? You're in this regime when the heat capacity for cooling is dominated by the envelope, and that corresponds to typical cores that are modeled on the Earth, and a hydrogen-helium envelope when you have about 5% or more of the total mass in these envelopes. More interesting is the second regime, where this is reversed. So if you have only a few percent of the total mass in your envelope, then you actually have more thermal energy stored in your core that's available for cooling than binding energy of your envelope. So what this means is the following. Your envelope will want to cool and contract, of course, but as it's giving away energy and wants to contract, basically the same amount of energy is being resupplied by the underlying core, and instead of contracting, your envelope basically stalls at this radius, and it keeps losing mass. So until you can drain basically enough energy from the core that both the envelope and core can cool significantly, you continue this mass loss. And so in this case, you can strip the entire envelope. Energetically, you have enough energy, and it gets easier and easier from an energy point of view, right? Once you lose half your first envelope mass, it's even easier energetically to lose the second half because you're not shrinking your rate of convective boundary. So that was really intriguing. So basically what planet formation would tell you, by default, you should expect a bimodal distribution of planet sizes, the ones that got to keep the hydrogen-helium envelopes and the ones that get to lose it. There's one other thing to keep in mind. It's not only an energy argument. There are planets for which they have enough energy to unbound their envelopes and lose them. However, that there's not enough time. So there could be not enough time because this mass loss timescale can take actually gig years. But in many cases, it actually turns out that the cooling timescale can catch up with the mass loss timescale. So basically, when your mass loss becomes long compared to your cooling timescale, then your envelope can cool and contract, and you can shut off any subsequent mass loss. And the reason for this is, again, because of this isothermal structure on the outside. Because you have an exponential tail in there, and so as soon as you increase the region over which this exponent is extending just a little bit, the mass loss rate drops significantly, and you can sort of shut off the mass loss, and you can cool a little bit more and save your atmosphere. So what I'll show you is the criterion for keeping most of the envelopes is that basically your cooling timescale has to become faster than your mass loss timescale. Okay, so much for theory. Let's try to put this all together. So with what I told you, you're not going to make a toy model, making your own planets. You can take the sort of observed mass distribution of planetary cores, which are a good proxy for the total mass of the planet, because these envelopes are only a small fraction of the total mass. Then I told you, you can calculate how much hydrogen helium they should accrete, how much they should lose during the dispersal phase, and then we can just involve them under this, what we call core-powered mass loss scenario. And indeed, what we found is you do get this bimodal distribution. So this red histogram is basically the outcome out of this very simple model. In this gray is a comparison with the actual observation. So what's intriguing is, just from a pure planet formation point of view, you seem to be able to reproduce this bimodal distribution that's observed in the exoplanet size distribution of the super Earth and Sub-Neptunes. We heard from James already, so this is by no way to say that this is the only thing going on. And we heard that foot evaporation can give you this bimodal distribution also. And I think we need to actually combine those two to really come up with a model that can do it all. But it's very intriguing to me that just planet formation would give you this. And this was just the first cut. My current grad student has done a more detailed comparison. So we not only have histograms, right? We now also have a two-dimensional distribution of orbital period and a size distribution. These are the observations you see up here. He repeated the same model, but just plotted this now in 2D to do a comparison. And again, I think he finds a very good agreement with observations. Specifically, we get a similar slope in this radius valley as the observation, it's very easy to understand where the slope comes from in the core-powered mass loss mechanism. I told you what separates the planets that keep the envelope versus the ones that lose is just whether the cooling time scale is faster or smaller than the mass loss time scale. So setting those two equal, we can solve for the slope. And these are complicated things because they depend on many things of your planet. But the nice thing is because one of them has this exponential in it. So to first order, all that really matters is the things in the exponent. And the things in the exponent is only this, just the mass of the planet, the speed of sound, and basically the size of your planet, the radius effective boundary. So we know those. And so you can rewrite them as a function of period and size, because that's what the observations are plotted in, and derive what the slope should be. It's just straight out of here. And what you get is this minus 0.1, which is in very good observations that actually James also showed from the Van Allen paper. Similar to the photoevaporation results, where exactly the slope will fall depends on the density. You can see this again just from the things that are in the exponent. So the location of the slope, we too find is consistent with rocky compositions, and that we found that at most you can have about 20% water fraction in those planets. Then, of course, you can do better. So far, we had assumed that all stars are exactly like the sun. So the first thing was to actually model the true stellar population of the Kepler data set. And by doing so, not surprisingly, but it's good to confirm, we got an even better agreement with observations. You can see this spreads out a little bit because the spread in stellar properties. But nothing revolutionary new here. We knew that it should be similar, so that's good. But what is nice is now we can ask questions and make predictions of how the core-powered mass loss mechanism should depend on various stellar properties and where it gives different results from what you would expect if this radius valley is shaped predominantly by photoevaporation. So I want to give you two examples. One is how it depends on the bolometric luminosity of the star. Here it's plotted as stellar mass, again, just because this is what's been done by the observers. So in the core-powered mass loss mechanism, why does a star matter at all? The star matters through its bolometric luminosity, because the insolation or the effective temperature that your planet has sets the outer boundary condition for mass loss. So this is where the star comes in. So what this means is if you have a higher luminosity star or a planet that has a higher insolation, you have a faster mass loss rate. And so in the end, you can strip a more massive core if you have a higher bolometric luminosity. So this means if you have, because of the mass luminosity relationship of stars, which is well measured in studies, more massive stars have higher luminosities. We find in the core-powered mass loss scenario that this radius valley moves to larger stellar masses, to larger planet sizes as a function of stellar mass. And we can even measure the slope. And this actually is in quite nice agreement with observations. We can again derive this analytically very simply, again, from exactly the same argument, same exponent. Again, you're just rewriting this because now you're writing this explicitly in terms of the insolation received, and you can analytically even derive the slope. But you can, of course, do this numerically also. This is one thing where we predict something quite different from photoevaporation, right? Photoevaporation, as we've heard from James, is driven by the X-ray and EUV radiation from the star. This is more strong relative to the bolometric luminosity for lower mass stars. So lower mass stars for a given bolometric luminosity should be more efficient at stripping planetary cores. It should be able to strip a larger core than higher mass stars for the same bolometric luminosity. And so when this data was interpreted by Yanxun Wu using photoevaporation models, to basically get this trend, she suggested that the underlying planet mass distribution needs to be have a positive linear correlation with the stellar host mass star to get this positive trend. So for us, we have the same underlying planet mass distribution, would say it's independent of stellar host mass, because we get this trend, if you wish, by default, just from the bolometric luminosity. So that's one way where there's quite different predictions. between these two mechanisms. There are several others, but this is another one which I think is quite clean. This is dependence on stellar age. So we heard from James that it's the young stars that are really active, right? It's the young stars that drive most of the mass loss, where most of the photoevaporation is happening. In the core part mass loss, this happens over gigayear timescale. It's basically continuously happen from basically the birth of your planet until today. So there are planets even today that are still being converted from sub-Neptunes into super-Earths. And so if you plot basically, this is now a relative occurrence of sub-Neptunes to super-Earths as a function of age. You can see if you go from 1 to say 10 gigayears, your planets still shrink. You can see this too here, but you also see that you get more and larger super-Earths because these are the Neptunes that are still stripped, sub-Neptunes that are still stripped and converted into super-Earths. So what this means is that if you can study these populations as a function of age, that we predict that the occurrence rate of super-Earths should still increase if you go from half a gigayear to a gigayear to several gigayears with respect to the sub-Neptune population. So, and that there will be a few planets today that you can catch in the valley losing mass right now, just because some of them have just the right timescales for that. So let me conclude. So planet formation itself seems to give you a bimodal distribution in planet sizes. So core cooling just by itself wants to either let you have these hydrogen-helium envelopes or strip you entirely. Light atmospheres that contain less than about 5% of the total mass of the planet can be stripped entirely because there's enough energy to do so, whereas heavy atmospheres, more than roughly 5% of the total planet's mass, will just cool and contract over gigayear timescales. The majority of the rocky exoplanets are basically fully consistent with having formed with a hydrogen-helium envelope. And then basically being stripped cores of what we see today. We find that these cores on average have densities quite similar to the Earth. So it suggests that they're not true water worlds. Maybe pointing to formation inside the ice line, but we'll see as we have better models and better data. Because the core part mass loss proceeds over a gigayear timescales, the occurrence rate of super-Earth with respect to sub-Neptunes will increase with time. Because core cooling does depend on the bolometric luminosity of the star, we predict that the radius valley should shift to larger planet sizes or masses as you go to increasing stellar masses because of the stellar mass luminosity relationship. We predict that there's no change in the underlying planet mass distribution, so that the typical planet masses are the same around a sun-like star and a star that's say 0.8 or 0.6 times the mass of the sun. So again, that's something that we can test observationally. And I think most importantly, I think in future work that basically we started, but it's still ongoing, is basically the effort to really combine the photoevaporation models and the core part mass loss models to correctly and completely model this atmospheric loss, because my suspicion is that probably this will be needed to correctly interpret the observations and make inferences, for example, about the planet's densities and their evolution. So thank you very much. And sorry about this crazy numbering. I don't know. I can just say it's my jet lag. Somehow this made sense some time ago.
Thank you very much, Hilke. Yes, there's a question. Please state your name and affiliation.
Dennis Sergeyev, University of Exeter. It's probably a weird question, but can there be a situation when an atmosphere of a planet being stripped away from one planet and then being gained by another planet?
It's a great question. I thought about this a little bit. I think it's hard in reality. So for stars, we see this happening all the time, or it's not so uncommon. I think it's harder for planets, and the reason is that unlike stars, a binary star that's close and can have mass transfer, your planets are not co-spatial for a long time because of the Keplerian shear. So they do come by, and they're not that far apart, but that's only a short time in their orbit, right? Because then the Keplerian shear, most of the time, is actually spent quite far apart. So for that reason, I think it's very unlikely to happen. Yeah.
Daniel from MIT. In the plot of planet radius versus period, the lower population, the average size seems to go down with period. So if these are supposed to be like rocky cores, why would they get smaller with increasing period? Is there like a reason from planet formation to expect that? Or?
No, so let me just make sure, are we talking about the same plot?
The one where you have period on the x-axis and
Yes.
radius on the y-axis.
It's not letting me go back. It's hilarious. It doesn't let me go back. So
Okay, only forward.
oh, this one is good, right? You mean this one, right?
Yeah, so the
And
lower
saying,
red blob.
Right, you're saying this goes down with period, right?
Or at least it looks like.
Yeah, so the reason is it gets harder because when you're further away from the star, you receive a lower bolometric luminosity, so it gets harder to strip the core. So it means you can only strip lower mass planets, and so that's why they look smaller. So the equivalent planets that would be here are still stuck in this model in the Sub-Neptune population, because the outer boundary condition that's given by the bolometric luminosity of the star is such that the mass loss rate is slower, and so you get stuck being a Sub-Neptune rather than being converted into a super-Earth. This is where that dependence on period comes from as you go to larger orbital periods. Does it make sense?
I guess yeah, maybe I'll have to think hard about it, but if I interpret the lower red blob as just a core that's like stripped of everything, I would assume that like everything that falls into that population is roughly going to have the same size, no? So like not like you're right in saying like some of them might not make it to that population at longer periods, but if you do make it to that population, shouldn't you have the same size regardless of period?
No, because there is this mass dependence, right?
Okay.
Because you have a colder outer boundary condition, your mass loss rate is lower as you go further away, so larger masses can still hold on to their envelopes, and that's why these guys get stuck up there. So if you would plot this in planet mass, you'll see that at each period you have the same planet mass distributions, but the ones that become super Earths are different depending on how far away you are from the star.
Interesting. Cool.
Yamina?
I was wondering, we think that in the process of planet formation, there are also a lot of giant impacts.
Yes.
So I was wondering how that, like, having impacts might affect this population.
Thank you for asking that question, because those impacts are my other big passion. Indeed, so giant impacts, actually, one of my PhD students that just finished did quite a lot of work on the atmospheric loss in giant impacts. And what he showed is that for hydrogen helium envelopes, they're amazingly good at stripping the atmosphere, which is quite different actually from sort of secondary atmospheres where you only get loss of 10 or 20% in typical giant impacts. And that's again actually because of the heating. So you have so much energy deposited in the core that you significantly heat the core and the envelope that you tend to lose it all for those sort of systems. So I would used to say that, oh, there can't be too many giant impacts because that will mess up our plot too much, but it's not quite so clear anymore, because if you really strip everything, you could hide many giant impacts in here and just be either a Neptune or a super Earth and not that much in between. I do think they happen at some level, maybe not quite as prominent as I believe they used to be, but I think the fact that he found that you tend to strip everything makes it more easily reconcilable with this very clean radius valley. So.
One last short question before the coffee break. Yes, please. Please state your name and affiliation.
So, Robin Wordsworth, Harvard. I was wondering, do you take radiative cooling mechanisms into account in your outflows? Do you think that's going to be important at all?
That's a great question. We thought about this a little bit, but I think it does need and deserves more attention. So the reason why you need both a star, so as James said so nicely, right, in the core part mass loss, the energy basically comes from the interior of the planet, both what's left in the envelope and the core. And that's basically providing the energy to lift the material sort of out of the potential well. However, it's cooling adiabatically, so it's not enough to just escape. And so this is why the star comes in again. So because you do need the photons, the volumetric luminosity, so not the hard photons, just the normal photons, to keep your gas at sort of the typical temperature you would expect. So as long as you can satisfy this, that you will roughly be in the naive equilibrium you expect, you're okay. But there can be cases, especially if you go far enough away from the star, where this assumption will break down. And that's definitely something that we started thinking about in more detail. Yes.
Okay, let's thank Hilke again.